Welcome. We're going to talk about projectile motion. Normally when we talk about projectile motion, or at least what you probably think about, is like throwing a ball up in the air, and if you sometimes maybe you've seen strobe photography where it would capture it at the different points in its path. And if you do it that way, which is kind of the more intuitive way, this is distance. You're throwing the ball up and it's landing somewhere far away from you. And then this is height. That's kind of normal 2 dimensions. What we often do in math class, especially when we first introduce this, is do it a more easily understandable way to do this. So we only reduce it to 1 dimension. If I throw a ball straight up and I did that same kind of stop photography, it might look like that going up and then maybe the same points coming down. But we can then graph it. Instead of doing distance in this direction, we can do time, and we can do height going up. So at each point in time, it's at a different height, and then it reaches its maximum amount and eventually starts falling again. And usually this will very much follow a parabolic path. So we know the parent function is x squared, and we know it essentially follows this, where this is our maximum vertex, and we have some number out front that is related to what this curve is. And for those of you who did the can rolling activity in the class, most of you got like 0.05 or something like that, 0.1, because it wasn't. It was going up a ramp and there was some friction involved. So that's just what that was about. So when we do this in projectile motion, we're typically doing it in the Earth's field, gravitational field. I'll give an example which is not, but generally it follows the same thing. We have an A value, which is always the acceleration due to gravity. Technically it's half that, which is a calculus problem in and of itself. But the numbers that we plug in for A, we actually know this, so that's important to understand. Whenever we do a gravitational problem in the Earth's field, we know that the A value is either negative 4.9 meters per second, 4.9, or it is negative 16 feet per second squared. And this meters per second squared. I think it's per second. So those are the 2 numbers we are choosing from, negative 4.9 or negative 16. And it just totally depends on, are we getting our answer in metric or in English units. Very often that will be determined what our initial velocity is and what our initial height is. Now notice these are 2 very different equations. And so these are interchangeable, but it depends on what the initial information are you given. Are you given the vertex, the maximum height, or are you given the initial velocity and the initial height? And so what that will typically look like, just as a reminder, so we throw something up in the air, we're measuring its path over time. Oftentimes the height, this S0, this initial height, is above ground. That makes the problem a little easier, or more interesting actually. We have some vertex that it will hit at some time, at some height, and then we finally very often will ask, at what time did it hit the ground again? So those are the questions that can be asked. So with that, let's do a problem. Okay, so rather than do something in the Earth's gravitational field, we're going to do something on something I call planet M, which conveniently has a acceleration due to gravity of negative 2 meters per second, which is going to make the math a little easier, or negative 6.6 feet per second, which I'm going to avoid because it's going to make things more difficult. So let's say we hit a ball straight up in the air on this planet M with the negative 2, and our initial velocity is 10 meters per second. And maybe we're up on a platform that's 12 meters high, and the ball's going to go straight up to some height, then come down and miss the platform and eventually land on the ground. So first of all, to plug this into our equation, this is pretty straightforward. Our height, y, is equal to negative 2, because I'm doing meters per second squared, x squared, plus 10, x, plus 12. And if I wanted to know at what time did this thing land, that would be pretty easy, because my graph looks basically like this. And that right there can easily be found using the quadratic formula, plugging in your A, your B, and your C. So that's somewhat trivial if you know how to use quadratic formula. If we want to figure out this vertex up here, there's 2 ways, and I'm going to kind of show you the more difficult way first, only because you should know how to do this. If I put this in vertex form, well, that'll be the number. But the problem with putting this in vertex form is I don't know how to deal with that number in front of the x squared. So I'm going to factor it out. I'm going to just pull whatever that number is out front, which means everything here needs to be divided by that -2. It's negative. You're going to have to flip all your signs. X squared, this could be a minus 5x. I often will leave that positive. That'll mess things up. And a minus 6. Okay? So now I'm going to complete the square on this. Y equals -2. All inside a parentheses world here. We're going to complete the square. So that's x squared minus 5x. Half of 5 is 2.5, and 2.5 squared is 6.25 minus 6. And if I add 6.25 in, I've got to subtract it back out to keep my expression equivalent. All right, so this ends up being y equals -2. X minus 2.5 squared is what that is, and this is a minus 12.25. And this would seem to be right. It looks like it's in vertex form. 2.5 seconds is what that is. X equals 2.5. And then this doesn't look right, because that looks like -12.25 is the height here. And the problem here is this needs to get distributed back out before this is truly in factored form here. Or sorry, vertex form. So I'm going to multiply it times both of these. I'm just going to leave it out front in front of the perfect square, because that's the way vertex form is supposed to look. And then this over here becomes 24.5. So from this I can see at 2.5 seconds this thing has a height of 24.5. Now that was actually kind of the hard way, because you actually should know a very quick way to find that number from our original expression. And the way we find out that number is -b over 2a. If we take our original problem and plug in our b and our 2a, that's -10 over 2 times -2. So this is 10/4 or 2.25. Sorry, 2.5. That is this. And then we hopefully would recognize, oh, that's the x value at that vertex. How can I find out the y value? Well, I can simply plug it back in to my expression. So I'm not going to work this out, but if I plugged in the 2.5 that I got from doing the -b over 2a into my original expression, that will generate the 24.5 that I got that way. So depending on what you're being asked to do, this is probably the quicker way. If you've got it in vertex form already, or you are forced to put it in vertex form because of some evil math teacher, then you've got it right there in front of you. But make sure you take a second look at that, and also make sure when you divide out by your negative number, this will always be negative, you flip the signs on these. That's an easy thing to forget. Okay, other kind of problem that you might get, still on planet M, which I'm going to call it EMM now. After 4 seconds, a projectile has reached its maximum height of 20 meters, and I realize that's ITS, not IT apostrophe S. It's, yes, that's the correct way to write it. Its maximum height of 20 meters. This is really difficult, because oftentimes we'll say, well, I know that the acceleration it's in meters, so for planet M it's -2, but my velocity and my starting point, I don't know that at all. And that's probably the question, is what was the velocity or the starting point, or when did it land? It seems like we don't have enough information. But the key here is maximum height. This is telling you that is the vertex. So the way you figure that out is you're like, well, y equals x minus 4 squared plus 20. I got to remember to put my a in, which is -2. And then if I want to work backwards to figure out these two values, I can plug in, I can expand it. Squared minus 8x plus 16, doing that in my head, hopefully that's right, plus 20. So y equals -2x squared plus 16x minus 32, which means plus 20, which means y equals -2x squared plus 16x minus 12, if I've done all my math correct here. which is interesting. It means this actually started below ground, which is possible. You'll see an example like that in a minute. And then the other question is, now that I know my velocity, my initial velocity and my starting point, I could also ask, when did it land? When is this point? And once again, I could take my my general form formula, use quadratic formula, or as a reminder, you could always take this original form back here and you say, well, that's where y equals 0. So you can say, well, that means 0 equals negative 2x minus 4 squared plus 20. And then it's a matter of minusing 20 from both sides, dividing by negative 2, taking the square root of 10. So my zeros are 4 plus or minus, that's a plus or minus, square root of 10. One of those is going to end up being negative because I started on the other side of 0. Oh, actually, no, they're both going to be positive because I was below ground when I started. So it's like this. I did that math really quick. Hopefully it's all correct. Okay, 2 more problems. This is turning into a little bit of a long video. You've got a ball thrown straight up at a telephone wire. This is on planet Earth, okay? And we're going to do it in feet only because I told you so, not because of anything specific to the problem. It passes a wire at 0.5 seconds, and on the way down, again at 2 seconds, what was the initial velocity and throw height relative to the wire? So basically, we've got a picture that looks kind of like this. We've got a wire. We're throwing something up, and it's coming back down again. Okay. This is essentially our axis, and we're given this time of 0.5 and this time of 2. So you can't see that. So essentially, they've given us our zeros. So take a second to think about what that equation would look like. And I'm going to write it out. X minus 0.5, x minus 2. This is very close. What are we forgetting? That's right, we're forgetting our a, which I've told you to do it in feet just because I said so. So that's going to be negative 16 out front, y equals. And then to find the initial velocity and height, once again, we'd expand it back out again. We get y equals negative 16 x squared minus 2.5 x in the middle plus 1 on the end. And so y equals negative 16 x squared, 32, I think that's going to be 40 x, and then a minus 16 is how far above, this is 16 above from where I threw it from is how far this is, was 16. Okay, I think that's right, 32 and another 8, I think that's 40. So there's my initial velocity. All right, almost done. Got a little quiz for you. Okay, on Earth, a ball is hit straight up at a velocity of 12 feet per second. The contact with the bat is 4 feet off the ground. How high does it go? When does it land? So try that, then I'll review the answer and you can freeze it. Okay. Going to factor out the negative 16. I'm going to get some very difficult numbers to work with. It might actually be easier to use a fraction here. Okay, but the process is the same. Half this number squared, got to minus it back out again. Rewrite it in factored form. I have to remember that minus doesn't make sense there. I need to distribute the negative 16 again. So I get this. This thing did not go very high. And then once again, I just plug back into the quadratic formula for my negative 16a, my b is 12, my c is 4. And I get 1 second. That negative value is because I started above 0, and therefore it thinks I had launched from the ground at a negative time. As a reminder, the easier way to find the maximum height, the positive 3.75 seconds and 6.25 maximum height, is simply do vertex form. We plug in our 12 and our negative 16 in, we get 0.3, that's written wrong, it's 3.7, no, it's 0.375. and then I plug it back in to find the 6.25 feet at vertex. That's more than enough. Thanks for hanging in there. Ciao.